Hey everyone, welcome back to my channel, and in this video we'll solve these two problems from NLM part of Pathfinder. These two questions are kind of related to each other as in like you need to know very well about the geometrical properties of a helix in order to solve these two questions, and that is exactly what we'll be doing in this video. And after watching this video, these two problems would make complete sense to you guys. If you enjoyed the solution, please like and subscribe. So let's begin with problem number one. In problem number one, we basically have to find the radius of curvature of the helical path. Okay. So let's say there is some particle that is performing circular motion in the XY plane. Okay. And this Z axis is perpendicular to the plane of the circle. Now, if we consider a frame of reference moving down with a velocity of V, okay, then to this person standing on this reference frame, this particle will appear to move in a helix. So now if I consider a point on this circle, then the velocity of this particle will be omega multiplied by r if the angular velocity of the circular motion is omega and the radius of this line is, let's say, r. Let's say if we give this particle a vertical velocity v, it will move along in a helix. Okay, so basically if we take a point somewhere on this helix, let's say this point, it will have two velocities. One velocity is perpendicular to this radial line. Okay, so I'm going to take this point so that it's easy to visualize it. This will have a velocity, let's say the omega is in this sense. So at this point, the particle will have a velocity of omega r into the plane, and also it will have an ascent velocity of v in the upward direction. In short, if we give the circular motion a vertical velocity of v, so the path of the particle will be helical. Okay. Now let's go back to this particle which was performing a circular motion. The only acceleration in this case is omega square r, which is opposite to the radius vector. Again, remember with respect to this person, this particle undergoes a helical motion. As this guy is in an inertial frame of reference, acceleration of this particle in both the frames will be same. The acceleration of this particle is only towards the opposite to this radial line, and its magnitude will be omega square r. If I write it here, the acceleration of this particle will be simply omega square r, and it will be opposite to the radial line that I drew. If I want to find the radius of curvature on a curve at any point, all I have to do is find the net speed at that point, square it, and divide it by the perpendicular acceleration at that point. So first of all, what is the speed of this particle at this point? It has a component v in the up along the z cap and omega r into the plane. So now as these two velocity components are perpendicular, so their net speed is going to be under root of v squared plus omega r the whole squared. Okay, now divided by the component of acceleration perpendicular to the velocity. Now observe something. So omega r is into the plane, v is vertically above. The net speed will also be in this plane that is perpendicular to the plane of the page, right? So you guys have to imagine this. So there is only one component of acceleration, right? Omega square r, and it is perpendicular to the net speed. So the a perpendicular is going to be simply omega square multiplied by r. So in the Pathfinder problem, they have given us a value of pitch. So let's discuss what pitch is. Our particle started from some point here. So we know helical motion is just a combination of circular motion and translation. So let's say the particle starts from this point and it starts traveling along the curve and it reaches this point. So as you can see, it has ascended a vertical distance h, and this is what we call as the pitch of a helix. So the time taken for one revolution in a uniform circular motion is 2 pi by omega, and as the ascension velocity is v, this pitch p we can write it as velocity multiplied by the time. And in the problem, pitch was given to be h, so I'm going to take that. Okay, now we have the value of v. So the radius of curvature comes out to be v squared, which is h omega divided by 2 pi whole squared plus omega r divided by omega square. Now as you can see, this omega square term gets cancelled out. So this is the radius of curvature of the helix. It only depends on the pitch of the helix and the radius of the circular motion. Okay, and that would be option number B. Now there are a few interesting geometrical properties of a helix. Let's consider the particle to be at some point here. So this particle will have two velocity components. One velocity component is the velocity of ascension, which is along the axis of this helix. And another component is, let's say if we draw a radial line from here, this velocity is going to be perpendicular to this radial line, and that will be in a direction something like this, and its magnitude will be omega r. And the net speed will be tangential. This is going to be the net velocity vector. As this omega r and v are always constant, right? Doesn't matter even if you take it here, The magnitudes of these are not going to change, which means this angle, let's call it theta, is also going to always remain same throughout the helix. Okay, let's say we call this point as point number 1. Okay, let's say we call this point as point number 2. Now, point number 1 and point number 2 I have taken in such a way that they're very close to each other. Very small displacement, I can call it as dl vector, let's say. So this dl will be comprised of two components. One is going to be because of the circular motion, and that, as I explained earlier, is going to be perpendicular to this radial line. And let's just call that distance as dx. Okay, and there will also be one more component of displacement, and that's in the vertical direction, and let's call that dh. And let's say this angle is theta. Okay, the angle between dl and dx. So if I draw it as a triangle here, so this will be dl, this will be dx, and this will be dh, and this angle is theta. So now the interesting part of our helix is that this angle theta will always be the same irrespective of which point you take. So let's say we took this point. Even here, this dl and this dx would make the same angle theta with respect to each other. Because of the reason that I explained earlier, the velocities remain constant. The speed of the particle remains constant. With the help of this, I can actually do something very interesting. So if I get rid of this, so let's say the particle started from point number 1 and it went to point number 3. So the particle's motion will be something like this. And now if I asked you guys the question that find the path length from point 1 to point 3 that this particle had to go through. So how do you find that? So well, you guys would do integral dl from point 1 to point 3, right? But you can also do something else. Okay, so let's say that I call this path length as some L. Now let's call the vertical distance between point 1 and 3 to be, let's say, h. So now I'm making a claim, which I'll prove a bit later. So let's say this distance is actually 2h. So the side length of this triangle is going to be 2h, and this base is going to be 2 times the circumference of the circular motion. Okay, and I'll explain it to you guys why is it this way. So now from this triangle you can easily find out the path length, and also this angle will also be the same theta that we discussed over here. Now why is it that way? I'll try my best to explain that. So if you guys, so actually this big triangle that we just drew, it is combined of these dx's, right? Individual dx elements. So you guys have to imagine this a little bit. Okay, so as I said earlier, this dx element is always tangential to the circular motion that we discussed earlier. If you integrate all that dx elements, now this is not tangential to the helix, by the way, this is tangential to the circular path. If you add up all these individual dx elements for one complete revolution, won't you get the circumference of the circle? So now as from 1 to 2, the particle had to undergo 2 circular motions. So the integral dx would come out to be 2 times of 2 pi r. Okay. And if you add up all the small dh elements from point 1 to point 3, you'll get 2h, where h is the pitch of the helix. dl elements is pretty straightforward, right? If you add up all the dl elements, which is tangential to the path of the helix, you'll get the path length, and let's just call it for now as L. And from this triangle, by using Pythagoras theorem, so this triangle is basically the combination of all the small dx's and all the small dh's and all the small dl elements. So if I zoom in on this big triangle that I just drew, this is going to be the dl element, this is going to be the dx element, and this vertical height of it is going to be the dh element. And as we discussed earlier, this angle between it is always theta. And that's why we can draw this triangle. So basically, in short, so let's say if we made up a question here. So let's say this point is A and this point is B. So there is an ant who wants to go from point A to point B, and find out the time that the ant takes, and it can only travel along the helix. So for that, we need the path length AB, right? So the ant will start traveling something like this, right? So how many oscillations did it complete? It completed 4 oscillations, right? So all you have to do is draw a triangle first and assume the path length to be L, and this distance is going to be 4 times 2 pi r, and this distance is going to be 4h, and you can get the path length using the triangle, and this angle will be theta. I mean, this is mostly just imagination, so I hope I could help you guys imagine this very well. If you have any doubts, you can comment down below. Now, keeping these geometrical properties in mind, let's try to solve this problem from Check Your Understanding. Okay, so let's read the problem first. So we have a bead that slides down a height h on a thin vertical rod. So this bead slides down this rod a distance h, and it's given that it takes time t1. So we can instantly write time t1 as square root of 2h by g, right? Because it's frictionless. So the only force, so its acceleration would be g. Now, and the same height on a rigid helix. Now this bead is over here. It's sliding down this helix, and it's given that it slides down the same height h as this bead on the left side. So let's try to analyze that. Now, as I said earlier, it descends, this particle, let's say it descends by a height h. So let's say this is the height h. So this is the path taken by the particle. So we can actually stretch it out into a triangle and call this the path length. So we need the acceleration of this particle in order to find the time taken. So we'll use the property that we just discussed above. So let's say this point is 1, let's say this point is 2. If we want the path length, helical path length of this particle from point 1 to 2, what will we do? We'll draw a triangle, and let's say the path length is L, and we know this height it descended by is h, and let's call this angle theta. So from this triangle, we'll get the path length from point 1 to point 2 as h upon sine theta. Okay, so this is equation number 1. So now we know the path length. Now we need the acceleration, right? And so let's say the bead is over here, and clearly we know this acceleration down the plane is simply g sine theta. So the time taken for the particle to come from 1 to 2, which is given in the problem to be t2, is square root of 2 times the path length, which is h upon sine theta, divided by its acceleration, that is g sine theta. And from here we'll get the answer as 2h root 2h by g divided by sine theta. So this is simply t1 divided by sine theta, right? Okay, so now the problem is still not done. Okay, so now the problem is still not done, but it's almost done. In the third part, now the rod is rigidly fixed along the axis of the helix. Okay, so we have this rod that is fixed on the axis of the helix, and on this there is a bead that can slide up and down, and it is tied with a light inextensible thread to another bead that can slide on the rod. Okay, so this bead is now connected to this bead on the rod with the help of a light inextensible thread. Now let's say the time it takes to descend by a height h is t3. So we have to express t3 in form of t1 and t2. That's the question. Also, there is a very important assumption. We have to assume the radius of the helix so small as compared to the length of the thread, so that the thread can assume to be almost vertical. Okay, so this bead over here can only go up and down, right? But let's try to, draw the FBD of this bead over here. Now, in the previous problem, we found out the path length. It was L, and this distance was h, right? And now in this problem, to this bead, we have attached another bead. And okay, now all we have to do is find the acceleration of the bead in this case, and just do square root 2L by A, and we'll get the answer. Okay, so let's try to find the acceleration of this bead now. So let's first assume the acceleration of this bead is A along the helix. So now as these two are connected by a light thread, if we assume the thread has some tension, then the acceleration of this bead along the thread has to be same as the acceleration of this bead along the thread. So now as we assume this acceleration to be A, this angle is also theta. Let's say this acceleration is A parallel, and A parallel will be equal to A sine theta. Okay, so the acceleration of this bead over here will be A sine theta downwards. Now let's write two F equals to ma equation. So first equation will be for this bead, and as we know, the force along the helix is going to be mg sine theta, plus there will be a t sine theta component because of this string. This would be equal to the mass of the bead times the acceleration, which we assume to be A. This would be equation number 1. And the second equation, let's write for this bead over here. So we can say mg minus tension T equals ma sine theta. So I am going to multiply the second equation with sine and add these two equations, so the tensions gets cancelled out, and I'll get 2 mg sine theta ma times 1 plus sine squared theta. And finally, we'll get the acceleration of the bead, which we wanted to be, divided by 1 plus sine squared theta. Now, as we have the acceleration, our problem is done. So so in this case, the time taken for the particle is going to be square root of 2. What is the path length? So the path length we found out in the previous part of the problem, that came out to be h upon sine theta. Upon the acceleration is 2g sine theta divided by 1 plus sine squared theta. So we have two equations, right? So t2 came out to be t1 upon sine theta, and we also know that t1 equals square root of 2h by g. What I am going to do is cancel out the 2's. H by g, I can write it as t1 squared divided by 2. H by g, I can write it as t1 squared divided by 2. So this sign and this sign would make what? Sine squared. And if you divide it into this, you'll get 1 plus 1 upon sine squared. So, and sine, I can just borrow it over from here. And finally, our answer will come out to be square root of t1 squared plus t2 squared divided by 2. So I hope that this video helped you guys to understand this concept. If you have any doubts, you can comment down below, and thanks for watching.